In this video, we're going to talk about low-level PV anomalies. Now, strictly speaking, PV anomalies can occur at any level of the atmosphere. But in order to conserve PV, we know that the flow must be frictionless and adiabatic. And so this is not quite true at the surface. And so the question is, can we come up with something that would be PV-like? That we could then identify PV-like structures at the surface to then be able to forecast through this lens better, or at least understand the atmosphere better through this lens. And so we've generally been talking about positive PV anomalies, and so we're going to see what we can do to generate something that is a positive PV-like anomaly near the surface. To do so, we're going to need to start with a cross-section. And so we're going to draw ourselves initially a box here, just as we've been doing for these PV anomalies. And then what we're going to do is we are going to consider this a positive theta anomaly. And so we want to consider, what if we have a warm sector in the middle of our cross-section? In order to really illustrate this, what we're going to do is we're going to draw some isentropes. And so we want to recall that when we're drawing isentropes, our warm air is in pockets and our cold air is in domes. And so we can draw that, and then aloft here, well above the surface, we're going to consider that we don't have any change in isentropes. And so again, we can label these here simply theta. If we're closer to the surface, it'll be colder, theta minus delta theta. If we're more aloft, theta plus delta theta, theta plus 2 delta theta, and so on. And so what we've identified here are cold regions and warm regions. Our cold regions are in our domes, and our warm region is in our pocket. And ultimately what we want to do is we want to talk about then the circulation that happens as a result of this setup. And so in order to do so, we're going to want to think about our zone where this is true. And so we're going to identify here kind of our segments of the atmosphere that we're curious about. And so I've drawn in our black dashed lines to consider that. And so now we need to consider, so if we have this warm anomaly, then what do we know about the flow? Well, if we're talking about temperature, then we're talking something about the thermal structure of the atmosphere. If we're talking about the thermal structure of the atmosphere, then we should be talking about things relative to the thermal wind. And so one of the things we can do is we can make a statement here based on the vorticity of the thermal wind given this positive theta anomaly. If this is all in fact the case, we know that within this zone, our thermal wind vorticity, or zeta sub t, must be less than 0. Now, why must it be less than 0? Well, we know we always want to keep the cold air to the left of our thermal wind. And so in this case, that would result in a thermal vorticity being less than 0, or anticyclonic thermal vorticity. And so then the question becomes, if this is the case, how can we relate this more to our regular geostrophic vorticity that we're usually used to working with? And so one way we can say that is with our zeta sub t, our thermal vorticity, that is equal to the difference in our geostrophic relative vorticity aloft minus our geostrophic relative vorticity below. Similar to the difference of our thermal wind being the geostrophic wind aloft minus the geostrophic wind below. And we can just do the work to get to our idea of thermal vorticity here. And so one of the things we can say, because we're just considering things near the surface here, is that aloft, we don't have any geostrophic relative vorticity. So zeta sub g aloft, we're going to define, so 3 lines here, equal to 0. If that is in fact the case, we know that then this term goes to 0, such that we end up with our relationship for this particular setup as zeta sub t equal to minus zeta sub g below. And so if we know that this is in fact the case, zeta sub t is less than 0, then this whole right-hand side must be less than 0. For this to be true, that means that zeta sub g below must be greater than 0. Well, what does it mean for zeta sub g to be greater than 0? This means that our flow should be cyclonic. So we can draw in some cyclonic flow relative to our positive theta anomaly, x into the board, dot out of the board, and we'll annotate that up here, into board, and our dot being out of board, or out of page as the case may be here. So what does this mean? Our positive theta anomaly has positive cyclonic geostrophic vorticity anomaly associated with it, which is awfully similar to what our positive PV anomaly is. Our only missing loop here is the fact that we haven't said anything about the static stability. Now, we can do so with a sleight of hand, talk about how our theta surfaces that intersect the ground are really connected below the ground. And if they are, through this sleight of hand, we can say that we also have an increase in static stability in this location. So our positive PV anomaly, or our positive theta anomaly, is acting just like a positive PV anomaly. This is great. This means that our positive theta anomalies are also associated with things like cyclones, and we can see this even more distinctly if we consider a typical mid-latitude cyclone. Let's go ahead and draw our L. Let's say we have a warm front off to the west, or the east rather, a cold front to the west. And let's go ahead and place this cross-section within this context. And so we're going to draw our cross-section such that A would be to the west, B to the east, and we'll annotate A and B on our cross-section. And knowing our typical northern hemispheric cyclones, we know that we have cold air behind our cold front, cold air ahead of our warm front, maybe slightly different than the cold air behind our cold front, and our warm air within the warm sector of the cyclone. And so our positive theta anomaly is associated with this middle part of our cross-section, associated with the warm sector of our cyclone. And intuitively, we should know that this should have cyclonic geostrophic relative vorticity associated with it, because we know that we have southerly winds in our warm sector. We have some sort of easterly winds ahead of our warm front, and northwesterly winds behind our cold front, such that we have cyclonic rotation. So in fact, what we're seeing here is coupling well with in our PV perspective as well as within our classic QG and just map perspective of how all these things are related. So one remaining piece is, how is this then related to upper level positive PV anomalies? That will be the subject of a future video. Thanks for watching.